Why does every bounded monotone sequence have a limit? Why does Bolzano Weierstrass work? Hidden behind all these beautiful results lies one powerful idea, the foundation of real analysis itself. The beauty of the Monotone Convergence Theorem will be unlocked and visually explained in this video. The concept of cluster points and its connection with the subsequential limit will be explained. The difference between the limit of a sequence and the limit point or cluster of the sequence will be explained. The idea of limit superior and limit inferior will be visually explained. How they are related will be shown. Their equality guarantees the existence of the limit of the sequence, or simply the convergence of the sequence. How does the Bolzano Weierstrass theorem work for sequences? How is it different from the set version of the theorem? How does it help in finding the limit of a sequence? All the answers are here in this video. Want to crack CSIR-UGCNET/JRF-GATEIITJAM-NBHM or PhD entrance exams? Then you cannot afford to ignore sequences and convergence. From subsequences to limit superior and limit inferior.
Uniqueness of the limit of a sequence. If a sequence converges to a limit L, then it is unique. Suppose not, that is, it has two distinct limits, L and M. That means L minus M is a non-zero real number. We apply the definition of the existence of limits Lm for the epsilon. Then we arrive at a contradiction. It means that our supposition is wrong. That is, our assumption that two distinct limits are there is wrong. Hence, the uniqueness of the limit of a sequence is established. Every convergent sequence is bounded. If a sequence converges to a limit L, then it is bounded. For epsilon value 1, all terms are inside the open interval L minus 1, L plus 1, except only finitely many terms. That means all terms starting from nth term is bounded. The remaining finitely many terms from 1 to n minus 1 is also bounded. Hence, every convergent sequence is bounded. Whereas the converse is false. So there are bounded sequences that are not convergent. Definition of subsequence of a sequence. A subsequence is formed by taking its terms from the original sequence without disturbing the order. This means if the fifth term of a subsequence is formed by taking the 10th term of the original sequence, then the 6th term of the subsequence should not be any term less than or equal to the 10th term. Mathematically, if n1 is less than n2 and n2 is less than n3 and so on, then A and K is a subsequence of the original sequence. Cluster point implies convergent subsequence. If C is a cluster point of a sequence, there exists a subsequence converging to C. By the definition of cluster point, every neighborhood of C contains infinitely many terms of the sequence. That means, given a positive integer n, there are only finitely many terms before an, and there are infinitely many terms after an. So, there exists n greater than or equal to n, such that the nth term is in the neighborhood. So if we take epsilon equal to 1 upon k, we can find a positive integer nk, which is strictly greater than the previous positive integer nk minus 1, and the nk is in the epsilon neighborhood of C. In this way, we have constructed a subsequence A and k converging to C. Limit inferior and limit superior of a sequence. From the nth term onward, if we find the infimum and call it Sn, then we have a non-decreasing sequence Sn of real numbers. Similarly, from the nth term onward, if we find the supremum and call it capital Sn, then we have a non-increasing sequence capital Sn of real numbers. The supremum of Sn starting n from 1 to infinity is called the limit inferior of the original sequence. It is exactly the smallest cluster point or the infimum of the set of cluster points of the original sequence. For every sequence, there exists a monotone subsequence. First, we define the notion of peak. A term of a sequence is called peak if it is greater than or equal to every other subsequent terms. There are two cases arise, finitely many peaks and infinitely many peaks. Case 1, infinitely many peak. Let the indices where the peaks occur be m1, m2, m3, and so on. So we have an increasing sequence of natural numbers, m1, m2, m3, dot, dot, dot. The corresponding terms am1, am2, am3, dot, dot is a monotone decreasing subsequence. Finitely many peaks. Suppose there are finitely many peaks and the last peak occur at n. Then for a natural number n, 1 greater than n, the corresponding term of the sequence an1 cannot be a peak. So there exists another natural number n2 greater than n1 such that an2 is greater than an1. The above process continues infinitely. So we have a monotone increasing subsequence. Monotone Convergent Theorem for real sequences. We only demonstrate for monotone increasing sequence, which is bounded. For monotone decreasing one, we can do similarly. If a sequence of real numbers is bounded, then it has a unique supremum. The sequence converges to the supremum. Suppose L is the supremum. For an arbitrary small and positive epsilon, we show that all terms an for sufficiently large n are inside the open interval L minus epsilon, L plus epsilon. This is done by the logical argument that L minus epsilon is not an upper bound, so there exists a positive integer n such that an is greater than L minus epsilon. Remember, only finitely many terms are less than an, and by the monotone increasing property of the sequences, all other terms is greater than an. But L plus epsilon is an upper bound of the sequence, so all terms are less than L plus epsilon. Therefore, all terms except for finitely many terms are inside the open interval. Hence, the sequence converges to L. Convergence and subsequences. If a sequence converges to the limit L, then every subsequence also converges to L. Conversely, if every subsequence converges to L, then the sequence converges to L. Assume an converges to L. Consider an arbitrary subsequence ank. The proof used the definition of convergence of sequence, and for subsequence, the sequence nk is a strictly increasing sequence of positive integers. The converse is straightforward because every sequence is a subsequence of itself. Bolzano Weierstrass Theorem for sequences. Every bounded sequence has a convergent subsequence. We shall demonstrate how the theorem is proved. We shall use the Monotone Subsequence theorem. That is, every sequence has a monotone subsequence. Then we use the Monotone Convergent Theorem, which says that every bounded monotone sequence is convergent.